Welcome to class of physics. In previous video, we studied about divergence and curl of a vector field. Now in this video, we are going to discuss about integral calculus using vectors that we call as vector integrations. In electrodynamics, we encounter several different kinds of integrals, among which the most important are line integral, surface integral, and volume integral. Now we are going to discuss three kinds of integrals: line integral, surface integral, and volume integrals. Let's see one by one. The first one is line integral. A line integral is an expression of the form integral a to b p bar dot dl bar. Here v is a vector function, or it may be a vector field, and gl is an infinitesimal displacement vector. The integral is to be carried out along the prescribed path from point A to point B. If the path is from a closed loop, then put a circle or integral sign. Here phi bar is a vector function. Let's take, there is a line. Now we have to integrate between two limits a and b. In this, the dl is small or infinitesimal length displacement vector, that called as displacement vector. Now this we call it as dl. Now the total value from a to b is obtained by the integral of this vector function phi. Suppose this line makes a complete loop, that is, for example, take it as a circle somewhat. So in this condition, what happens? Actually previously the point B is here, but in this example the point B is here. The starting point and the ending point both are same, so that's we call it as B equal to A. So in these conditions the vector function will makes a loop. Then the integration of this vector functions is represented by an circle over the integral sign. So like that we have to represent the line integral. Then we have to calculate. One of the best example for this line integral is work done. What is the expression for work done? So work done is f dot dl. Yes. Here f is a vector function, that is force, and dl is the displacement vector. So in these conditions we are going to perform the line integral operations. And next one is surface integral. A surface integral is an expression of the form integral phi dot dA. Here phi indicates the vector functions and dA is an infinitesimal patch of area with the direction perpendicular to the surface. Again, if the surface is a closed loop like a balloon, in such case put a circle on the integral sign. So here for the closed surface to write the surface integral of this form. In this diagram there is a surface area. This is surface area that is represented by a vector function phi. Now we have to make a surface integrations. For this we are going to take a infinitesimal patch of area. So here small area we are considering. This we call it as infinitesimal small area. The direction of this is perpendicular to the surface. This take it as normal. So now the integration of phi dot dA will give the total surface area. Suppose if it forms a closed surface, so like a balloon or a sphere or a box, closed box, so in such conditions I have to represent this surface integral by a circle on the integral sign. So this is surface integral. Next one is volume integral. A volume integral is an expression of the form p dot d tau. So this is tau, Greek letter tau. Again here p is a vector function, d tau is infinitesimal volume element. What is the volume? So volume is calculated by the multiplication of breadth, height and length. In Cartesian coordinates, these breadth, length, height are represented by the coordinates x, y, z. For that, in Cartesian coordinate, d tau is the volume element, infinitesimal volume element, that is obtained by the multiplication of these three vector components dx, dy and dz. So here is the mistake, it is dy. Dx, dy, dz will give the infinitesimal volume element. So then we can write the volume integral of a vector functions as p dot d tau. P is a vector functions. In component form, we can write that vector function as vx x cap, vy y cap, and vz z cap into d tau. Now we have to integrate each term with d tau. For that, write separate integrals vx x cap d tau, vy to y cap d tau, and vz z cap d tau. So this is the volume integral. Here x cap, y cap, z cap are the unit vectors. These unit vectors are considered to be a constant terms. For that, write these unit vectors outside the integral. Then we can write like this: x cap integral of vx d tau, cap integral of vy d tau, z cap integral of vz d tau. This is the volume integral. So like that we can write the line integral, surface integral and volume integral in terms of integration symbol. The next is Gauss divergence theorem and Stokes theorem. So these two theorems are very important in electrodynamics: Gauss divergence theorem and Stokes theorem. So actually here these two theorems are provided to convert one integral form to another integral form, maybe surface to volume and surface to line, line to surface, line to volume. Like that we have to convert one form of integral to another form by using these Stokes and Gauss divergence theorem. First one is Gauss divergence theorem. Okay, let's see one by one. In vector calculus, divergence theorem is also known as Gauss theorem. Here, and the name of Gauss divergence theorem is divergence theorem. It relates the flux of vector field through a closed surface to the divergence of the field in the volume enclosed. There are two important terms are it relates the flux of vector field through a closed surface. So here one side is flux of vector field through a closed surface. This is going to relate with the divergence of the vector field in the volume enclosed. These two are divergence of vector field in the volume enclosed and flux of a vector field through the closed surface. So how to state this Gauss divergence theorem? The Gauss divergence theorem states that the vector's outward flux through a closed surface is equal to the volume integral of the divergence over the area within the surface. Again, the statement itself, the vector outward flux through a closed surface is equal to the volume integral of the divergence. Volume integral of the divergence is represented by del dot V. Okay. Over the surface, which is this, over the surface within the surface. So here it is volume integral. For that, again write the symbol volume integral, then it is deta. This relates to this second sentence. What about the first sentence? Vector outward flux through a closed surface. Again, this is represented by closed surface, means integral, the circle over the integral. Here the S indicates is a surface. Then flux is V dot d. This represents a flux. Now these two are the equals. What it is? Circular integral over the surface, V dot dA equal to del dot V to d tau. Here both are the same. This is in terms of surface integral and this is in terms of volume integral. Like that we have to convert. Next one is Stokes theorem. Similarly, Stokes theorem relates the surface integral of a curl of the vector field to a line integral of vector field around some boundary surface. Again, this Stokes theorem relates surface integral of a curl, the vector field, to a line integral. That means it will convert surface integral to line integral. The statement of this Stokes theorem is, the surface integral of the curl of a function over the surface bounded by a closed surface will be equal to the line integral of particular vector function around it. The first statement is, surface integral of the curl of a vector function over the surface bounded by closed surface. In first sentence, it represents there is a closed surface and surface integral of the curl function. If it is curl, then we can write in terms of curl, that is del cross of a vector field. Here of vector field is V dot. It is surface integral, for that with respect to dA. Now we can write this. This is related to first. The second statement, that is equal to the line integral of a particular vector functions. Line integral of particular vector function means there is a line integral of a vector function. This is a vector function. Line integral is represented by dl bar. Okay, so this is around it, and also it is closed surface. For that we have to represent by circle. By equating these two, then we will get integral of del cross V dot dA equal to V bar dot dl bar. Like that we can convert the surface integral to volume integral, so line integral. Please practice these two theorems, Gauss divergence and Stokes theorems. These two are the important in Maxwell's relations, deriving the Maxwell relations. Okay, so this is enough for today's class. Now take an assignment question. These assignment questions are helpful for the next class. Yes. State Gauss law in electrostatics, Gauss law in magnetism, Faraday's law, and Ampere's law. Okay. These four laws are important for Maxwell's relations. So one is Gauss law in electrostatics, second one is Gauss law in magnetism, third law is Faraday's law of electromagnetic inductions, and the fourth one is Ampere's circuit law, Ampere's law for current in conductors. Okay. Thank you.